Hello everybody and welcome to the session. Well, we have been talking a lot about differentiation, how to differentiate different types of functions, and what are all the strategies to do that to obtain the differentiation of a certain differentiable function. Now it's time to actually apply all those learned concepts in our questions. Let's begin with this particular exercise. Let's talk about the very first question. For 2 marks, it says that differentiate sine square x with respect to e to the power cos x. This is one function, this is another function. If I am saying that let ux be the function that is sine square x and vx be the function, again because it is a function of x only, e to the power cos x. One thing is sure, that the question is asking me to differentiate ux with respect to vx. Is this directly possible? Of course not, because ux is not directly a function of vx, right? Ux is not directly a function of vx, they are not directly related, but there is a link which is relating them, which is acting as a parameter here. What is that? Sine square x is a function of x, e to the power cos x is a function of x. This x is serving as my parameter, which is acting as a link to connect the two functions ux and vx, which are not directly connected. Okay? So in here, what is the very concept of differentiating a function in parametric form? If I wish to differentiate ux with respect to vx, where ux and vx are individually functions of the same parameter x, then this is equal to d by dx of ux. You can clearly see ux is differentiable and it is a differentiable function of x, so I can find out the differentiation of ux with respect to x, divided by d by dx of vx. I am so sure about the existence of d by dx of vx because vx is also a differentiable function. Cosine is differentiable, exponential function is differentiable, composition of two differentiable functions is differentiable, so vx is differentiable, and therefore I can find d by dx of vx as well. By the very chain rule which we use in order to differentiate functions in parametric form, d by dvx of ux is d by dx of ux upon d by dx of vx, provided this denominator differentiation is not equal to 0. This will be what? D by dx of sine square x, which is nothing but sine x whole square, divided by d by dx of e to the power cos x. Again by chain rule, what do you get? D by dx of sine square x. This is nothing but d by d sine x of sine x whole square into d by dx of sine x. That's the chain rule for composition of functions, right? What is this? Exponential of cos x. Again composition, again chain rule. D by d cos x of e to the power cos x into d by dx of cos x. D by d sine x of sine square x. What is this? It's almost like d by dx of x square, which is 2x. So this is 2 sine x into d by dx of sine x, which is cos x, whole upon d by d cos x of e to the power cos x. You know d by dx of e to the power x is e to the power x. Here cos x is playing the role of that particular argument. So d by d cos x of e to the power cos x is e to the power cos x. And d by dx of cos x is minus sin x. I am only considering those values of x for which denominator is not equal to 0, otherwise this particular differentiation won't be defined. Fine, and therefore obviously if that is the situation, I can cancel out my sin x because I am only taking those x's for which sin x is not equal to 0. So therefore I can cancel sin x from numerator as well as denominator. What am I left with? I am left with minus 2 cos x whole upon e to the power cos x, and that is what is the differentiation of sine square x with respect to e to the power cos x. It is minus 2 cos x upon e to the power cos x. Moving to the next question, we have differentiate cos inverse of 1 minus 2x square with respect to x if restriction over x is given to you, that x is strictly greater than 0 and strictly less than 1. Now in here, if this is the function I wish to differentiate with respect to x, one thing is sure, that inside this the argument of cos inverse is a polynomial function which is always differentiable. Cosine inverse, you know that it is always differentiable because every inverse trigonometric function is differentiable. Composition of two differentiable functions is again differentiable, and therefore I am first of all very sure that this is a differentiable function. What I am not able to see is what is its differentiation. That is what we need to fetch. So here I am saying that let fx be equal to cos inverse of 1 minus 2x square. For sure this is a differentiable function. I need to obtain its very differentiation. In here, of course, somehow I will be interested in replacing this x and substituting it with something which can actually make this expression very, very easy. If you remember the identity 1 minus 2 sine squared theta, 1 minus 2 sine squared theta is cos 2 theta. Here I can get cos 2 theta, in the case of which I will be having cos inverse of cos 2 theta, which is a very familiar expression to you and me, as we have dealt with these type of expressions in inverse trigonometric functions a lot. So what I would be doing is, let's see can we do it or not. I'll substitute x equal to sine theta. Why am I able to do that? Please try and understand this concept very nicely. You don't need to do all this in your paper, but it's very important for you to understand what is the logic behind substituting x as sine theta. When I talk about the graph of the sine function, I'm only interested in this much portion, so I'll just draw this much. This is 0, this is pi, this is your 1, this is minus 1. X, it is being said, is strictly lying between 0 and 1. X is strictly lying between 0 and 1. Fine, strictly lying between 0 and 1. You can see that corresponding to angles varying from 0 to pi by 2, corresponding to theta varying from 0 to pi by 2, sine function is strictly increasing. Corresponding to this section of the domain, sine function is strictly increasing. That means it is 1, 1 as well as on 2. Right? You can see this by the graph. That means corresponding to, what I am trying to say is that sine x or sine theta from 0 comma pi by 2 to 0 comma 1 is 1, 1 and on 2. If it is on 2, as you can see from the graph, if it is on 2, this implies for every x belonging in 0 comma 1, there exists unique theta belonging to 0 comma pi by 2 such that sine theta is that x. That is the definition of on-to-ness. For every x coming from 0 comma 1, there is a theta for which sine theta is x. Theta is coming from this interval. That means you give me any x coming from this interval of 0 comma 1 open, there is definitely a unique theta for which sine theta is that x, and that is the logic behind being able to write x as sine theta for all x coming from 0 comma 1 open interval. Because x is equal to sine theta, where if x is coming from 0 comma 1 open interval, then sine theta, that means is coming from 0 comma pi by 2 open interval. Is it understood? I am only talking about the principal value branch. I am not moving ahead than this interval. That is the purpose, okay, here. So, after this, what next? Once we have decoded this substitution and the logic behind being able to substitute x as sine theta, we can just plug it in over here. We have fx equals cos inverse of 1 minus 2 sine square theta, because x square is sine theta whole square, which is sine square theta. As I had already told you, 1 minus 2 sine square theta is cos 2 theta. Can I after this write 2 theta or not? Cos inverse of cos 2 theta is 2 theta. Is that true? Not always. You should know that cos inverse x is a function from minus 1, 1 closed interval to 0 comma pi closed interval, and this is satisfying this property that cos inverse of cos x is x only for all x coming from 0 comma pi closed interval, and cos of cos inverse x is also equal to x for all x coming from the domain of cos inverse, which is minus 1, 1 closed interval. What is being used over here? Cos inverse of cos of an angle. Cos inverse of cos of an angle is equal to that angle only when that angle is coming from 0 comma pi closed interval. Is that true in this case or not? Only when 2 theta is going to come from 0 comma pi closed interval can I write cos inverse of cos 2 theta as 2 theta. So in here, if this is actually theta, not sine theta. If x is coming from 0 comma 1, that means sine theta is coming from 0 comma 1, that means theta is coming from 0 to pi by 2. If theta is coming from 0 to pi by 2, 2 theta is going to come from where? If theta is greater than 0, less than pi by 2, clearly 2 theta is greater than 2 into 0 and less than 2 into pi by 2, which is pi. This means that yes, 2 theta is coming from open interval 0 comma pi, which is already contained in closed interval 0 comma pi, and therefore I can write this as 2 theta. Also, if x is sine theta, can I write theta is sine inverse x? Let me tell this to you. X is sine theta if and only if theta is sine inverse x. This is only true when theta is coming from minus pi by 2 closed interval and x is coming from minus 1, 1 closed interval. See, your concepts from inverse trigonometry should be very clear to be able to conclude all these results. Here you can see theta is coming from 0 comma pi by 2, which is a part of this interval. It is contained here only. And x is coming from 0 comma 1 open interval, which is a part of this interval itself. And therefore, yes, I can write from x equals sine theta, theta is sine inverse x. So this will be twice of sine inverse x. If fx is boiling down to twice of sine inverse x, what is f dash x? D by dx of 2 times of sine inverse x is 2 times d by dx of sine inverse x, which is 1 upon root over 1 minus x square. Fine, already x is given from 0 to 1. That means already x is lying in minus 1, 1 open interval, for which d by dx of sine inverse x is this value. So my answer is this. Is it clear? So there were a lot of concepts that were used in this question. Of course, you don't need to write every concept in the solution when you are attempting this question in the paper, but for your thorough understanding, this is very much required. Question number 3 says, show that this function is continuous at x equals 0. If I talk about this function, it is fx equals 2x minus mod x. You all know that mod x is equal to x if x is greater than or equal to 0, and mod x is equal to minus x if x is less than 0, and therefore my function is a branch function which has boiled down to x and 3x. Here x is greater than or equal to 0, here x is less than 0. If I wish to show this function is continuous at 0, I will have to show that limit x tends to 0 f of x is f of 0, and f of 0, f at 0 is 2 into 0 minus 0, which is 0. So I basically have to show limit x tends to 0, f of x is 0. That means I have to show left hand limit is equal to right hand limit is equal to 0. What is left hand limit? Left hand limit of f at 0 is limit x tends to 0 from the negative f of x. If x is approaching 0 from the negative side, that means clearly x is less than 0. For that situation, fx is equal to 3x. So this is equal to limit x tends to 0, 3x. 3x is a polynomial which is always continuous. So limit of a polynomial function at a point is the value of that polynomial function at that point, which is 3 into 0, which is 0. We've done this. So left hand limit is coming out to be 0. Talking about right hand limit of f at 0, what would that be? It is limit x tends to 0 from the positive f of x. If x is coming closer and closer to 0 from the right hand side of 0, that means x is greater than 0. For that x, fx is equal to x. So this is equal to limit x tends to 0 of x. Again, x is a polynomial function of degree 1. Limit of a polynomial at a point is value of that polynomial at that point, and that is 0. So right hand limit is also 0. You are getting left hand limit of f at 0 is equal to right hand limit of f at 0 is equal to the value of the function at 0. So my function is continuous at 0. Moving to the next question we have, it is given that for this particular function, Rolle's theorem is satisfied for this given value of c, find the value of a and b. If it is already being given that this function is actually satisfying the Rolle's theorem on this interval, that means this function is continuous in this closed interval, this function is differentiable in this open interval, f of 1 is equal to f of 3, all this is holding for this function, and there is therefore existing a c for which f dash c is equal to 0. That is what is the Rolle's theorem, and that c also is given to you as this. There is existing this c for which f dash c is equal to 0. This is the meaning of Rolle's theorem holding for this particular function. What is f of 1? It is 1 plus b plus a. 1 plus b plus a. What is f of 3? 27. 3 into 3 is 9, so 9b and 3a. F dash c, what is f dash x? It is 3x square. So f dash c, 3c square plus 2bx plus 2bc plus a into, what is the differentiation of ax? It is just a, so plus a. Fine. This is equal to 0. This is f dash c. 3x square plus 2bx plus a, in place of x put c, 3c square plus 2bc plus a equals 0. 27 minus 1 is 26, 9b minus b is 8b, 3a minus a is 2a. This is equal to 0. 2 comes out common, you're left with 13 plus 4b plus a equals 0. And what is this? 3c square. C is already given to you. 2 plus 1 by root 3 whole square plus 2b, 2 plus 1 by root 3 plus a. Let's resolve this. You get 3 multiplied by 4 plus 1 by 3 plus 4 by root 3 plus 4b plus 2b by root 3 plus a equals 0. So what do you get? You get a plus 4b, 3 into 4 is 12, 3 into 1 by 3 is 1. So 12 plus 1 is 13, so you get a plus 4b plus 13 plus 3 into 4 by root 3. 3 into 4 by root 3 is 4 root 3. Isn't it? 3 into 4 by root 3 is 4 root 3 plus 2b by root 3 is 0. Already a plus 4b plus 13 is coming out to be 0. So here I will be putting 0. I am left with 4 root 3 plus 2b by root 3. Here I can multiply and divide by root 3. I will be getting 4 into 3 by root 3. This 4 I can write as 2 into 2. Now I can take out common 2 by root 3. If I take out common 2 by root 3, I am left with 6 plus b, which implies b is equal to minus 6. If b is minus 6 and 13 plus 4b plus a is 0, a is going to come out to be 11. So you get a is 11. That's how the value of a and b is computed for this particular function for which the Rolle's theorem is being satisfied on this interval. Next says find d square y by dx square if x is this and y is this. Now see, in order to find double differentiation of y with respect to x, I should either have y as directly a function of x, which I will first differentiate and then another time differentiate. But here y is not directly a function of x. In fact, y is a function of t and x is also a function of t. So t over here is playing the role of a parameter, which is linking both y and x together, and it is with the help of that parameter I will be able to differentiate y with respect to x, because directly there is no connection between y and x. So what is d by dx of y? That is dy by dx. It is d by dt of y upon d by dt of x. Same thing, the differentiation technique for functions in parametric form. d by dt of y is 280 upon d by dt of 80 square. Fine. 2a comes out, it's constant, d by dt of t is 1 upon a comes out, d by dt of t square is 2t. 2a cancels out, you're left with 1 by t. Obviously, I'm taking a as non-zero quantity. So, once you have differentiated y with respect to x, it's coming out to be 1 by t. Again, you wish to do the same. You wish to compute d by dx of dy by dx, because this is what is equal to d2y by dx square. This means you wish to compute d by dx of 1 by t. Now, please try to understand this carefully. If x is equal to 80 square, this means x is a function of t. X is a function of t, so you can clearly compute dx by dt as d by dt of 80 square, which was 280. From here, either you can say from here that if dx by dt is 280, then dt by dx is 1 by 280. If dx by dt is 280, then reciprocal of it is dt by dx, which is reciprocal of 280, which is 1 by 280. Or another argument for this is, if x is a function of t, can I say t is also a function of x? Yes, of course I can say that. Why? Because if x is 80 square, t square is x upon a, which implies t is square root of x upon a. T is clearly a function of x. T is a function of x. So I am interested in differentiating t with respect to x, which I can do. This is d by dx of under root of x upon a, which is d by dx of x upon a to the power half. This is equal to what? 1 by 2. X upon a to the power 1 by 2 minus 1 into d by dx of x upon a, which is 1 upon a, d by dx of x, which is 1. This gives you 1 by 2 times root over x upon a into 1 upon a, but root x upon a is t, so you get 1 upon 2a t. By this also you are getting d by dx of t is 1 upon 2at, or directly if you have dx by dt, you can write dt by dx is 1 upon 2at. By any of the concept you can write this. Why am I telling this to you? Because over here you are wishing to compute d by dx of 1 by t. 1 by t is a function of t, and t, as I told you, is a function of x. T is a function of x. So if you wish to compute 1 by t's differentiation with respect to x, you will have to use the chain rule of writing differentiation of 1 by t with respect to t multiplied by differentiation of t with respect to x. So let's do that. Directly you cannot compute this differentiation because t is not direct function of x. 1 by t is not direct function of x. 1 by t is first a function of t, t is a function of x. So here you write d by dt of 1 by t into d by dx of t. So 1 by t differentiate with respect to t, then differentiate t with respect to x. What is this? This is t to the power minus 1. d by dt of t to the power minus 1 is minus 1 t to the power minus 2, which is minus 1 by t square. And what is d by dx of t? d by dx of t in this form or in this form, in any form if you calculate it, is 1 by 2at. So your answer is minus 1 by 2at cube. This is the very value of d2y by dx square. It is minus 1 by 2at cube. Fine. Obviously, t, if it is coming in the denominator, a is coming in the denominator, they are all non-zero values. Clear? Next question says that if cos x whole to the power y is equal to sin y whole to the power x, find dy by dx. Now, clear indication is there of what? Of logarithmic differentiation, isn't it? Function to the power another function, function to the power another function. So I will be saying, applying log both sides, obviously log to the base e. What do you get? log of cos x to the power y is equal to log of sin y to the power x. By the property of log, I know this is equal to y log cos x is equal to x log sin y. Now you differentiate both sides. Differentiate both sides with respect to x. What do you get? Of course, see, this is one function of x, this is another function of x. One function of x, another function of x only, because first it is a function of y, then it is a function of x. So indirectly it is a function of x. Differentiating both sides with respect to x, this is product of two functions, product of two functions. I will be using the product rule. First function into differentiation of second function plus second function into differentiation of first function equal to same thing. First function differentiation of second function plus second function differentiation of first function. So what do you get? Y d by dx of log cos x. Log cos x is first a function of cos x, then cos x is the function of x. So first differentiate log cos x with respect to cos x, which is 1 by cos x, and then multiplied by differentiation of cos x, which is minus sin x, plus log cos x into d by dx of y, that is dy by dx, equal to x d by dx of log sin y. Log sin y is first of all a function of sin y. So differentiate log sin y with respect to sin y, that is 1 by sin y. Then sin y is a function of y, so differentiate sin y with respect to y, which is cos y. Then y is a function of x, so you have dy by dx, so you stop. Actually, we had to bring dx in picture, so you stop here. Plus log sin y into d by dx of x is 1, so it is just log sin y. Fine. Bring everything related to dy by dx on one side. You can see all this is concerning dy by dx. So you have dy by dx common, log cos x, and here you have minus x cot y. Minus x cot y, because it's coming to the left hand side of the equality sign, minus x cot y. This is equal to log sin y plus y tan x. And you have your answer of dy by dx. It is log sin y plus y tan x whole upon log cos x minus x cot y. Clear? This is your answer. Let's move to the next question. We have, if this function is continuous at 0, find the value of k. Now it is given that the function is continuous at 0, that means limit of this function at 0 is equal to value of this function at 0. So I am saying limit of fx as x approaches to 0 is value of this function at 0, and value of this function at 0 is k. So k is nothing but the value of the limit of f at 0. So k is limit x tends to 0 of fx. Now when x is approaching to 0, it is not equal to 0. It is not equal to 0. So this definition of fx will be used, which is log of 1 plus ax minus log of 1 minus bx whole upon x can be written like this, right? Now what I can do is, I can distribute the limit on both these individual functions. Why am I doing that will be clear to you in a while. This is limit x tends to 0, log of 1 plus ax whole upon x minus limit x tends to 0 log of 1 minus bx whole upon x. Right? Limit of difference of two functions is difference of the limit of those two individual functions. Provided these two limits are existing, I am sure they are existing, you will just notice in a while. Now what I am trying to recall over here is, this is resembling a very, very important famous formula, that limit x tends to 0 log of 1 plus x whole upon x is 1. If you have such an expression where an argument is being added with 1 of log, same argument is in the denominator and that argument is approaching to 0, then value of this limit is 1. Here I have log of 1 plus ax, not x. So argument is not x, it is ax. I need the same thing in the denominator and same thing should tend to 0, then this entire limit will be approaching to 1. So in order to build that, I multiply and divide by a. This a can be pulled out of the limit, you are left with a times limit x tends to 0 log of 1 plus ax whole upon ax. Something like this is created, log of 1 plus argument upon argument. The only thing I need is that argument should tend to 0. Right now x is approaching to 0. If x is approaching to 0, any constant multiplied by x is also going to approach to 0. So x approaching to 0, x approaching to 0 is the same thing. I have got the structure of this formula, and so in place of this entire limit I can write 1. A is already here. Minus. Again same thing. Here I have minus bx. So actually I can write this as plus minus b times x. So I have 1 plus minus bx. Minus bx is what I want over here. So I will be multiplying by minus b, dividing by minus b. And if x is approaching to 0, clearly minus bx is also approaching to 0. Not a problem. So this minus b will be pulled out of the limit and you will be left with limit minus bx tends to 0 log of 1 plus minus bx whole upon minus bx. Log of 1 plus an argument upon the same argument, provided that argument is tending to 0, the limit is 1. So you get minus b into 1. So you are left with a plus b. K should be equal to a plus b for this function to be continuous at 0. That's the answer. Let's move on to the next question. We have, if f of 2 is 4 and f dash 2 is 1, then find this limit. Okay. In order to use f dash 2 as equal to 1, I should have the very value of f dash 2 in this expression, which right now is not present. Value of f dash 2 is limit x tends to 2 f of x minus f of 2 upon x minus 2. This is what is f dash 2. Somehow I need to create limit x tends to 2 fx minus f of 2 upon x minus 2, which is not here. So what I do is limit x tends to 2 x f of 2, then you have minus twice fx. So what I do, I subtract 2 times f of 2, add 2 times f of 2. Already you have this. Okay? Whole upon x minus 2. What is the result of doing this? Let's see. Limit x tends to 2. F of 2 comes out common. Here you have x minus 2 upon x minus 2. Plus 2 comes out common. F of 2 minus f of x whole upon x minus 2. I want fx minus f of 2. So this will be, let me write it like this, that minus comes out common, you have fx minus f of 2. It's the same thing. Either write plus over here f of 2 minus f of x or minus over here fx minus f of 2. So you have fx minus f of 2 upon x minus 2. Of course, limit will be distributed on both these expressions. This is limit x tends to 2. This x minus 2 will be cancelled out. Why? Because x is close to 2, not equal to 2. This is a non-zero quantity. I can very easily cancel this out. Limit x tends to 2 of f of 2 minus 2 is going to come out of the limit x tends to 2 fx minus f of 2 upon x minus 2. Is it clear? Limit x tends to 2 of f of 2, this is a constant function, so it is going to remain the same. This is f of 2 minus twice of, what is this, limit x tends to 2 fx minus f of 2 upon x minus 2. This is f dash 2. F of 2 is given to me as 4, f dash 2 is given to me as 1, 4 minus 2 is 2, and that's your answer. Clear? Next question says that find f dash x if this is your fx for all x between 0 and pi. What is the relevance of x being 0 and pi will be clear to you in a short while, but one thing is sure, that this function requires the concept of logarithmic differentiation to be differentiated. So I have y as sin x to the power sin x, applying log x to the base e both sides. Applying log to the base e both sides, what you get? You get log y to the base e equal to log sin x to the power sin x. This will be what? Log y is equal to sin x log sin x. Clearly you know the next step, differentiate both sides with respect to x. So what do you get? 1 d by dx of log y. Log y is a function of y is a function of x. So first differentiate log y with respect to y multiplied by differentiation of y with respect to x. Chain rule. Here it is product of two functions, d by dx of sin x into log sin x. First function into d by dx of log sin x. Log sin x is a function of first sin x. So differentiate log sin x with respect to sin x multiplied by d by dx of sin x with respect to x, which is cos x. So first function into differentiation of second plus second function into differentiation of the first. D by dx of sin x is cos x. Here I am interested in cancelling this out. Can I do that or not? Of course I can. Why? Because x is lying between 0 and pi. If you recall the sine graph, this is 0, this is pi. If x is strictly lying between 0 and pi, that means it is not assuming the value 0, not assuming the value pi. Then in between, at any angle between 0 and pi strictly, it is forever attaining positive value. It is 0 at 0 and at pi, but it is not equal to 0 and not equal to pi. It is between 0 and pi strictly. So for all those angles between 0 and pi, sine is strictly positive. So if sine x is strictly positive for all x coming from 0 and pi, I can always cancel this out. It's not a zero quantity. So I am left with what? Dy by dx. Let me write it over here. Dy by dx therefore is equal to y cos x plus cos x into log sin x. Cos x plus cos x into log sin x. Y is what? Sin x to the power sin x. Cos x comes out common. Inside you have 1 plus log sin x. And this is your final answer. Clear? Next question we have, show that this function is continuous at x equals pi. If you carefully focus upon this function, it is a composition of two functions, isn't it? It is a composition of two functions. I can say, let hx be equal to sin x plus cos x. Let me take this as gx. And hx be equal to mod x. Then with this definition, HOG of x is h of g of x, which is mod of sin x plus cos x. Right? If this is gx, what is the structure of HOG? From here to here is my g, from here to here is my h, where this is g and this is h. I have to show HOG, which is this function, is continuous at pi For that, if I show G is continuous at pi and H is continuous at G of pi, then HOG will be continuous at pi. So I have to show G is continuous at pi and H is continuous at G of pi. That's the concept behind differentiation of function, which is composition of two functions. Or rather than that, I should say this is the concept behind continuity of function, which is composition of two functions. Right now we're talking about continuity, not differentiability. So if I have to show, first of all, G is continuous at pi, I have to show as x approaches pi, Gx approaches G of pi. First of all, what is G of pi? G of pi is sin pi plus cos pi. Sin pi is 0, cos pi is minus 1, 0 plus minus 1 is minus 1. G of pi is minus 1. This is first thing. Then I have to show that limit of Gx as x approaches pi is G of pi. What is limit of Gx as x approaches pi? So limit as x approaches pi, sin x plus cos x. You know that sin x is a continuous function throughout the real line, cos x is a continuous function throughout the real line. So the sum of two continuous functions is also continuous throughout the real line. And I know limit of any continuous function at a point is value of that function at that point. So this is sin pi plus cos pi, which is 0 plus minus 1, which is again minus 1, which is equal to G of pi. So limit x tends to pi, G of x is G of pi. I have got G is continuous at pi. Now I have to show H is continuous at G of pi. That means as Gx approaches G pi, H of G of x should approach to H of G of pi. What is H of G of pi? It is H of G of pi is minus 1 and H of minus 1 is mod of minus 1, which is 1. Fine. So H of G of pi is 1. I have to show that H is continuous at G of pi. H of G of pi is 1. Let's see what is limit y tends to H of G of y, H of y. Right? This is minus 1 actually. This will be minus 1. What I am trying to say is, as y is approaching to minus 1, is H of y approaching to H of minus 1 because this G of pi is minus 1. As y is approaching, I am taking this as y is approaching to minus 1, H of y should approach to H of minus 1 is my aim. H of minus 1 is what is H of G of pi, which is 1. So limit y tends to minus 1, H of y is limit y tends to minus 1 mod y. You know this is equal to what? Limit of mod is mod of the limit. So it is, because mod is a continuous function, so it is mod of limit of y as y tends to minus 1. Y is a polynomial function, it is continuous, so limit of a polynomial function at a point is value of that polynomial function at that point. This is mod of minus 1, which is 1. So what I do, I replace y by gx, y by gx approaching to minus 1. Minus 1 is G of pi. This is coming out to be equal to 1, which is H of G of pi. So I have got as Gx approaches G pi, H of G of x approaches H of G of pi. So I have got H is continuous at G of pi. So G is continuous at pi, H is continuous at G pi. Therefore, HOG, which is mod of sin x plus cos x, is continuous at pi. Is it clear? This is how you tackle this question based upon continuity of composition of two functions. So please revise all these 10 questions very nicely. They have used a lot of concepts related to this chapter as well as other chapters, like especially inverse trigonometric functions. Okay, I hope the concepts are very clear. That's it from my side.